Recording's on. Here we go. So, as we just discussed, right, there's our progression of the model of the atom, and we end up here with Schrodinger, right, his electron cloud model of the atom based on the idea of probability, right, that there are certain areas around the nucleus where we're more likely to find electrons, but the possibility exists they could be anywhere, okay? And yesterday, just sort of to reiterate a little bit, because I was messing with this map a little bit more, so this is an interactive map showing population density throughout the United States based on census data from 2010. Okay, so right, we can see that state by state there are certain states, right? The darker it is, the more people that are there, right? So we can see that there are certain states that have more population density than other states. Okay. All right, so more states, there are some states that have more population density than other states, but let's zoom into a state that we know a little bit better, right? So let's zoom into Ohio, okay, and there we are, okay. So Ohio itself has a pretty high density of population, right? More so than like West Virginia or Indiana or something like that. But if we zoom in a little bit more, right? So if we go to like counties, and I think we showed you this yesterday, but I'm going to get a little bit closer here in a second. All right. So by county, zoom in a little bit more, right, we can see here that there are certain parts of the states. Come on. There we go. That there are certain parts of the state, right, that even though when we looked at it from far away, the whole state had a pretty high population density, when we look at the state a little bit closer, there are areas where we see more population density than other areas, right? You know, you got your three biggies, right? This one up here, and then this one in the middle, and then this one down here, right? Are we good with those three? Right. Yeah. So, but then over here on the side, right, getting closer to West Virginia, we see a lot of lighter colors, right? And that population density isn't quite as great. Even though Ohio as a whole, there's a lot of people, right, and fairly densely populated compared to places like Montana or Idaho or something like that. But when we look closer, we see that maybe not so much, right? And then let's zoom in even closer, right, to some place that we're probably a little more familiar with. Okay. So we got this. Right? Let's go even closer. Okay. That if we get closer to Cleveland, right, and zoom in on that Cleveland area, there are even parts, even though on the bigger map, this whole area looked to be pretty dark, right? There are areas, some places where there's just not much there, right? And if we zoom in maybe even a little bit more, so let's go now and change it to this one, place. Okay. Change this up a little bit, okay. Oh, sorry about that. If we look here, right, even though this area is dark all around it, there are certain areas where there's not much. Anybody know what's going on right through here? Valley View and down this way. Anybody know what's there? Okay. Cuyahoga River, right? That's where the river runs, and it's big. Right? A lot of it is metro parks, right? And there's the valley where the river runs comes right up through here, right? There's not a lot of people that live there, right? Yes, there are lots of people around it, but even in this area that is very densely populated, there are some areas where we don't see very many people at all, okay? Keep that in mind as we go through here and start talking about what we're going to talk about today, okay? Good? All right. So, today's lesson is, first I'm going to do this and close this. Today's lesson is called Location of Electrons in the Quantum Mechanical Model. Okay? First, do we notice the pun that I've put onto this title slide here today? Yeah, I don't know if it's a pun really, but you know. What do I have to do here as far as titling this presentation. Okay?
Technically, there's no exact location of
Right.
an electron.
I can't tell you that this is where electrons are going to be, right? But Sarma, we talked about that we're going to talk about what today in relation to what you said before?
Probability.
The probability. Locations where we're most likely to find electrons, keeping in mind, right, that they could be anywhere. Okay? So, like we talked about yesterday, this work all comes out of Heisenberg and Schrödinger, right? That Heisenberg comes up with his uncertainty principle, that there's no way mathematically that we can tell the exact location of an electron and its speed at the same time, right? And that then leads to Schrödinger's development of his wave equations, which reveals area of high electron density. So, I made some changes to this presentation. I think I updated them all in your outline, but if there's something that's not quite making sense, let me know. Okay, I think I updated your outline to reflect the changes, but if it doesn't quite make sense, let me know. Okay. So, Sarmat, as we said before, these areas, as you said before, these areas of high electron density or high probability we call orbitals. Not orbits, right? Not like Bohr. Okay? Bohr said, right, Jotham, that Bohr said that those orbits are like rungs on a ladder, right? You're either here or here. But that's not the case now, right? We have an area where we're most likely to find electrons, but maybe not totally. Okay? So, the task then becomes, well, how do we identify these areas? Like we saw on the map, even certain areas that look to be very densely populated, within those areas, there's not that much there. Okay? And that's what we're going to find here today. So, just like we did on the map, we're going to start big and go small. All right? So the first way, or the way that we identify the quote-unquote location of the electron, or these orbitals, is by a set of numbers that we refer to as quantum numbers. Are we done right? So we identify these areas of high probability density, these orbitals, by a set of quantum numbers. If you want to think about it, it's kind of like an address for an electron. Okay? You have an address. Does that mean that's where you're going to be? No. Are you there a lot? Yeah. And there's a high probability that you'll be at your address, but that doesn't mean you're necessarily going to be there, right? So, we identify these orbitals, these probable locations, by a unique set of quantum numbers. They provide an address for the electron. Remember, it's not the exact location, just a most probable location, or an area of high probability. Each orbital, each area of high probability is designated by a set of 4 numbers. And those numbers are unique to that specific area. There's no other area around the nucleus that has the same set of quantum numbers. Just like there's no other house that has your unique address. Right? If you live on a main road that has kind of a common name, like let's say you live on Canterbury, okay? And you live at, 529 Canterbury Road. Is it possible that there's another 529 Canterbury Road somewhere in the United States? Sure. But is there another 529 Canterbury Road, Westlake, Ohio in the United States? No. Each orbital has a unique set of numbers that identifies it from all the other orbitals, all the other places where electrons could be. Okay, so keep that in mind as we go forward. All right, good there? Okay, so we start big and go small. First quantum number we refer to as the principal quantum number. Okay? The fact that it says principal, right, that means that it's important, right? The first, or whatever it is. Okay? We use the lowercase letter n to represent the principal quantum number. The principal quantum number identifies the main energy level where the electron is found. Principal quantum numbers identify large areas. If we look at this drawing, okay, we can see that there's a big dark spot kind of in the middle, right? And then there's sort of a break. Is it completely barren? No, right? But there's not much going on there. And then there's another big darker spot, right? And then there's another area where, maybe not much going on, right? And then there's another darker area here. These areas, the dark areas, are our principal energy levels. And we identify them with the principal quantum number. If we relate this to your address, what would that sort of be like? What would the principal quantum number sort of be like as far as your address is concerned? Eddie?
The digit in the address?
No, way too specific. Right? Mark?
Like, they could be, nothing much sense of say, like, street name.
It's a little too specific too. We'll see in a little bit.
Your house?
No, way too specific.
State?
This is kind of more like a state or a city. All right? Remember on our map of Ohio, there were like those three big dark spots, right, for Cleveland and Columbus and Cincinnati, right? Those kind of relate to these like three big dark spots here. These are big areas where there is a high probability of finding electrons, okay? So these are like your cities, right? They're like a big area where we find a lot of probability of finding electrons, okay? That's what the principal quantum number tells us, all right? Principal quantum numbers go up by 1. So this is the first principal energy level. This is the second principal energy level. This is the third principal energy level. And it just kind of keeps going up the farther we get out from the nucleus. Okay? Now, something that we sort of kept from Bohr, right? So Jotham, before you told us that those electrons could be on rungs of the ladder, right? What did those rungs correspond to, or what did they represent?
Where the electrons are.
Yes, but it also told us something else, though. It's not just where, it also told us something else. Laura, go ahead. The energy, right, or how much energy those electrons have. That's the case here as well. Electrons that reside in this principal energy level don't have very much energy. Electrons that reside here have more energy. Electrons that reside here have more energy. Okay? So it keeps going up as farther we get away from the nucleus. All right, good there? I think I have that written down, actually. Right? Orbitals closer to the nucleus that have lower principal quantum numbers have electrons with lower energy. That will become more important when you get to chemistry and you start talking about spectral lines and things like that. We're not going to do that in this class, but there's a reason that we came to that conclusion of how that electrons higher up have more energy, electrons closer down have less energy. Okay? All right. Good so far. So we said that these principal energy levels represented by the principal quantum number represent kind of like a city, right? But before we got into this, what did we see when we zoomed into the city? What did we see when we zoomed into the city? Is it all densely populated? No, right? That even within these areas of high density or high probability, there are certain areas that are more densely populated than other areas. And that's the case with our electrons as well. We refer to those as energy sublevels. Within the principal energy level, there are areas where there are greater electron density. Like we talked about on that map of Cleveland, right? There are certain areas that are very densely populated, but then there's other areas that aren't really densely populated. It's all Cleveland, but it's not quite the same from place to place. Okay? And we start seeing that there are areas that have more possibility of being populated than other areas. We refer to these areas as sublevels. So, the sublevels we distinguish by letters. The first sublevel is called S. And we will see here that those letters correspond to a shape as well. Okay? So, this is where you might have to fill in some things as we go along. Okay? So the first sublevel in each PEL, that's principal energy level, okay, is S. Right? So, if we take a look at a picture, and you guys don't have this picture, okay, but we see that there's an S sublevel in the first principal energy level. Then we call that 1S because it's the first S level. And then the next one out has 2S, and the next one out has 3S, okay? And we just kind of keep going farther and farther and farther, okay? Good there. All right. I'm going to start an interactive picture here to hopefully represent this. Okay? All right. Nucleus. Right? Nucleus is going to be the black one. All right. So, just outside the nucleus, there is an area of high probability of finding electrons. Why is there a high probability of finding electrons just outside the nucleus? Mark, go ahead.
Because the electrons, they want to be closer to the center because there's less energy there.
True. What else might be pulling them towards that center part?
The nucleus, because it has a positive charge.
Right? Positive charge on the nucleus, negative charge on the electrons. That results in less energy. That area is highly populated. Okay? So, we'll give that there. Oop. And see if we can make this here. We're going to make this one actually not as transparent. We're going to fill it. I'll make it a little more transparent than that. Right? So we can still see the nucleus there. And let's make it like light blue. Kind of like that. How's that? Does that work for you? All right. So this is our first principal energy level. Okay? Good there. There is another principal energy level that resides outside of that. Okay? Now, will all the electrons crowd to the middle and surround the nucleus? Suzanne says no. Why not, Suzanne? You're right, by the way.
Because there's not enough room.
Okay, there's not enough room, okay? But there's a reason why there's not enough room. Electrons are really small, right? So they don't need a whole lot of room. But there's a reason why all of the electrons that exist in an atom don't exist in this little blue space. Why?
Because if two electrons are next to each other, they try to separate.
Why?
Because two negative charges don't.
Okay. Yes, electrons are attracted to the nucleus because it is positively charged and they're negatively charged. But they're also repelled by each other, right? So this mixture of orbitals, these areas of high probability, are a balance between how close can those electrons get to the nucleus, but still kind of being apart from the other electrons, right? And that's why they settle into certain areas. That's why there are areas around the nucleus where there's a higher probability of finding electrons, and in areas around the nucleus that there are lower probability of finding electrons. It's not just a free-for-all, right? There's two forces that are kind of working there. That attraction to the nucleus and the repulsion from all the other electrons. Got it? So each electron's got to find its niche, got to find its little place. Where can I settle while I'm still attracted to the nucleus, but kind of standoffish from all these other electrons? Okay? So, we got an area of high probability at the base, at the beginning. And then, we've got another area outside of that. Alright, so, let's fill that one in. Let's make this one maybe more reddish. Okay. And then outside of that area there, there's a spot like that. Okay? And then, there's a third level that's outside of that level. Let's make this one. Anybody got any requests? Color they want to make this one? Purple might be a little bit too much close to the other two. I was gonna make green. That was kind of what I was thinking. So we'll make this one like a crazy green like that. Right? Okay. Keep in mind, this is a three-dimensional situation. I'm drawing it in 2 dimensions, but it is 3-dimensional. Okay. All right. I'm gonna add one more on this so we can use it a little bit later on. Okay. And let's go. Okay, good there? Great.
Is the probability density higher in the inner rings or outer
Ah.
rings, or is it equal?
What we will find is that just like if we look at different cities, okay, depending on the amount of space those electrons have, we will see that certain principal energy levels are more populated more densely than other areas. And that if there's more space, there's a uneven distribution because these electrons have a little more space to move around. Does that make sense?
Yeah.
If we go back to this map, okay, this is what Cleveland looks like, okay? But, let's zoom out a little bit, okay? Let's go over here to this spot right here, okay? Okay. So, you know where I'm at now? This is New York City, right? A smaller space, right, especially Manhattan, is a much smaller space than even Cleveland is, okay? But if we zoom in, right, the closer and closer that we get, right? Come on, Matt. All right? There are certain areas, even within there, where there's more density population than other areas, okay? Here, okay, this area right here, there's not a whole lot of population density because there's a bunch of like work buildings, you know what I'm saying? But when we get farther out, we see that there is more density, right? This is like Brooklyn over here, I'm pretty sure. I'm going to go right this way, okay? But anyway, so how densely populated an area is does depend on how big it is because there's more room to spread out and stuff like that, okay? So, Andy, going back to that, right? If we go back to that first level, right? How densely populated do you think that first ring is going to be?
Not as populated as the outer rings.
There's not as many electrons there, but what is the probability of finding an electron there?
Oh, greater.
Greater because of the whole positive attraction to the nucleus, right? There aren't as many electrons there, but they are confined to a smaller space because of that whole attracting the electron. Does that make sense?
Yeah.
Okay. All right. So now let's slide this over here. Get this out of the way, and we'll slide green out of the way. Let's focus on red. Okay. Red is a bigger area than blue. How many electrons are we going to find in that red area compared to the blue area? Mark?
Probably some more.
Probably more, and that's the case. But what we find out is that even within that red area, they are not evenly distributed. Okay? So we talked about that there is a certain area here that we call the S sublevel. And it looks kind of like a sphere like that. Okay? And that's what we were looking at, not there, but here. Okay? But just outside of this S sublevel is something that we refer to as the P sublevel. Okay? The first principal energy level, the blue dot or the blue sphere that we drew on the previous picture, doesn't have a P sublevel. Why? It's not big enough. Okay? But once we start getting out from the middle of that, from close to that nucleus, there's more space, more electrons can be there, but what we find is those electrons will settle in certain spots. Okay? we refer to the p sublevel as having a value L equals to 1. And we'll talk about L values here in just a little bit. Maybe not today, maybe tomorrow. Okay. P orbitals look like this. They have this kind of figure 8 shape to them. Okay? So, what does that mean on our drawing? If we go back here, right? So in this red level, we got this kind of circular part. We call this the S sublevel. Okay? But if we add another electron into the mix, right, what we find out is that electron sort of starts congregating just outside that circle. It can't break into the circle. Why not?
Because the electrons are repelling each other.
Repulsion. Okay? So it goes just kind of outside that circle. Let's say we add a fourth electron, or let's say we add a third electron to this mix. Okay? Where do you think it's going to go? Any guesses? Mark, good.
Even farther outside. That
Is it going to go here? Andy, what do you think?
It's gonna go on the other side,
Here. Why, Andy?
because if we were on the left side next to that one, they would repel.
A lot of repulsion there, right? But that next electron settles in on the other side, right? When you kind of put this all together, what do you get? Kind of that figure 80 shape, right? Okay? If we throw another electron into the mix, right? Here. If we throw another electron into the mix, here. Does that make sense? That balance between how close are we to the nucleus versus how far are we away from all the other electrons. Okay? Does that make sense? We refer to these as the P sublevel. And what we find out is that if we go up to the next level of green, right? Okay? Green has an S sublevel. That's kind of spherical. Okay? And then it has P sublevels as well. More space, more electrons, right? But they still try to space themselves out. Not an even distribution. Good there? Okay. What we find out then, actually let's hold on to that. All right. Next, outside of the P sublevels, there is the third sublevel that we call the D sublevel. Okay. Third sublevel is called the D sublevel. D sublevels don't start showing up until we get to the third energy level. I'll show you that in the picture in just a second. Okay? And there's a fourth sublevel. It's called F. All right? F I'm not going to draw for you, but D I'll draw for you. Okay? All right. Good with this? If we go back to our picture, right? Now, on this third sublevel, right? I messed up. Yeah, I'll do it later. All right, here, right? Now we start finding areas kind of like here. Yes, I know they're out of the green circle, but they're really part of that green circle, okay? Just outside of those P sublevels, where we start seeing more electrons settling in because of that balance between the attraction of the nucleus and the repulsion of the other ones, okay? This, ooh, too much. All of these are actually all together. And they go right on top of this. Kind of like one of those, you know, like those Russian dolls that like stack on top, they stack into one another, you know? That's kind of what this is like, okay? And that within these big areas, there are areas where we're more likely to find spots, Okay? Good for now? You okay with that? D orbitals have sort of like an X shape, whereas p orbitals are kind of like a figure 8. D orbitals are more like kind of an X shape. Okay? That's kind of what they look like there. And at the bottom of page 2, and we'll wrap this up for the day, at the bottom of page 2, you have a summary of the S sublevel, the P sublevel, and the D sublevel. F sublevels are the last one. They're crazy to draw, so we're not going to draw them. Okay? But we'll wrap it up for there. We'll pick it up from there tomorrow, and hopefully do some practice stuff. Okay? Good there? All right.